Hello everyone. Today we are going to present our MCA-330 ya oğlum nasıl okuyorum?
Kanka 330 o desene.
Tamam 330 mu diyeyim?
330 de amına koyayım. Niye böyle?
Tamam, heyecan,
Everyone today
heyecan
we are
yaptım.
going to present our
He-
MCA 300
heyecan yaptın. Baştan.
Yapma
3'ten
oğlum.
say. Tamam say. Çok çabuk.
3 2 1.
Hello everyone. Today we are going to present our MCA-330 robotic project, a camera-based line-following robot simulation. Our project was developed using ROS2JZ Gazebo Sim and Revis 2. The package name of our project is Lion Follower Robot. The main purpose of the project is to simulate a small differential drive robot that can automatically follow a black line track inside a gazebo environment. After the slide presentation, we will also demonstrate the working simulation and show the robot following the track in real time. The objective of this project is to simulate a mobile robot, make it follow a black line automatically, and visualize the robot data using ROS2 tools. At first, we tested the basic robot motion using the CMD-Val topic. This helped us verify that the Gazebo diff drive plugin and the ROS Gazebo bridge were working correctly. Then we focus on the actual line following problem. One important point is that a 2D LiDAR connects detect the black line because LiDAR measures distance, not color. Because of that, we used a downward-facing camera for real black line detection. Our final decision was to use camera-based centroid decision. This means the robot is not following fixed distance or hard-coded waypoints. Instead, it detects the black line from the camera image and adjusts its movement according to the directed line position. If there is a gazebo screenshot on this slide, this image shows the final simulation environment where the robot follows the black rectangle track. This slide shows the main software components of the project. We use ROS2JZ for nodes, topics, parameters, messages, and the line system. Gazebo Sim is used for the physics simulation, robot model, world design, sensors, and diff drive plugin. The ROS-GZ bridge package connects Gazebo topics with ROS2 topics. For example, it bridges CMD-Val, OROM, TF, scan, joint states, and camera image topic. The line follower controller is written as a Python node. This node releases the camera image, process it, and publishes velocity commands to CMD-Val. For image processing, we use NumPy. This allows us to threshold the image and calculate the line centroid without using CV bridge. Reviews is optional, but it can be used to visualize the robot model, TF frames, odometry, and LiDAR scan data. Now, the second presenter will explain the robot model, Gazebo world, and the camera-based line direction method.
Thank you, Emir. The robot is modeled as a small differential drive platform. It has two main wheels, one on the left, one on the right. These wheels are controlled by the Gazebo diff drive plugin. The plugin subscribes to CMD-Val, which contains the linear and angular velocity commands. The robot publishes odometry data on ODOM and transforming information on TF. The robot also has a 2D LiDAR sensor. The LiDAR publishes scan, but in this project it is mainly used for visualization and possible future improvements, such as obstacle avoidance. The most important sensor for line following is downward facing camera. It publishes images on line camera, image raw. This camera looks at the ground and allows the control to detect the black line. If the slide contains a robot model or sensor screenshot, this screenshot shows the robot body. The wheel structure and the camera placement. The gazebo world contains a black rectangular track on the ground. The robots start directly on the lower segment of this black line. We also designed the environment to look more like robotics test arena. There are outer walls, cones, banners, crops and decorative objects in the inner area of the track. However, these decorative objects are visual only. They don't have collision blocks. This means they don't have physical effect on the robot movement. This was an important design choice because the robot should be controlled only by the line follower algorithm, not by connect with obstacles. Another important constraint is a color. Since the camera detector searches for black pixels, only the actual track should be black. The decorative objects were designed with other colors so that the robot doesn't not confuse them with the line. This slide shows the remaining ROS2 topics used in final simulation. The CMD val topic carries geometry twist messages. This is the velocity command sent from our controller to gazebo diff drive. The line camera image row. The line camera image row topic carries the camera image. This is the main input for the line follower node. The ODOM topic provides robot odometry and TF provides transform data. The scan topic provides lidar data and joint states provides wheel joint state information. During test we use commands such as ROS topic hertz, line camera image row and ROS2 topic echo CMD val. This command helped us verify that the camera was publishing data and the controller was sending velocity commands. This slide explains how the robot detects the black line. First node receives an image from line camera image row. Second, the image is converted to grayscale. The code supports RGB, BGR, RGBA, BGRI, and mono image formats. Third, the node selects a region of interest or ROI. We don't need to process the full image. The lower and middle part of the image is more useful because it shows the track area near the robot. Fourth, the black line is extracted using thresholding. In our final setup, pixels darker than the black threshold value consider the black line's pixels. Finally, the node calculates the center of the black pixels. This centroid is compared with the center of the image. The difference between them becomes normalized line error. If the line is centered, the error is close to zero. If the line shifts left or right in the camera image, the error changes and the controller uses this error to steer the robot. Now Ece will continue to explain control logic, testing results and live demonstration.
Thank you, Ahmet. Now I'm gonna continue with control logic. The controller converts the image error into robot velocity commands. If the black line is visible, the robot moves forward and adjusts its angular velocity. The angular velocity is calculating using this formula: angular.z equals steering sign kp line error. Here kp controls how strongly the robot reacts to the line error. The steering sign parameter controls the direction of correction. If the robot turns away from the line, this sign can be flipped. The robot also reduces forward speed when the error becomes large. This helps the robot handle turns more smoothly. If the line is lost, the robot stops moving forward and slowly rotates to search for the line again. In our final working version, the parameters are speed 0.10, kp 0.9, steering sign -1, black threshold is 80. If the robot misses turns, the speed can be reduced to 0.08. If the robot turns in the wrong direction, steering sign can be changed to the 1. In the final working version, Gazebo Sim successfully launches the decorated arena and the robot model. The downward-facing camera publishes image data on line camera image row. The line follower node detects the black track from the camera image and publishes CMD val commands. The robot follows the black rectangular track without using hard-coded waypoint distances. This is important because the robot is using real camera-based feedback. The decorative inner and outer objects are visual only, so they do not affect robot motion. If there is a terminal screenshot on this slide, it shows the ROS topic outputs used to verify the system. For example, CMD-vel shows the velocity comments and line camera image row confirms that the camera is publishing image data. To conclude, we successfully built a camera-based line following robot simulation using ROS2, Jazzy and Gazebo Sim. The main achievement is that the robot follows the black line using a downward-facing camera and image processing. The key lesson is that LiDAR cannot detect a black line based on color. For true line following, a camera or an equivalent line sensor is required. For this work, the controller parameters such as speed, copy, ROE, and threshold can be tuned for smoother behavior. We can also add a debug image output to visualize the detected centroid drag directly. Another possible improvement is to use LiDAR for obstacle avoidance while keeping the camera for line following. Now we will demonstrate the working project. Now we are going to run the simulation. First we open the terminal and go to our workspace. Then we source ROS2, Jazzy and the workspace. After that we launch the project. When the simulation starts, Gazebo opens the decorated test arena. The robot starts on the black track, as you can see. The robot uses its downward-facing camera to detect black line. The controller calculates the line position in the camera image and publishes velocity comments to SIMD-vel. As the robot moves, it's correct its direction based on the detected line error. When the line is close to the center of the camera image, the robot moves mostly straight. When the line shifts to one side, the robot changes its angular velocity to return to the track. We can also verify the camera topic by running this. As you can see, the topic hertz. This shows that the camera is publishing image data. We can check the velocity command with this prompt, and you can see the outputs. Here we can see the robot receiving linear and angular velocity commands. This provides that the robot is not simply following a predefined path, it is following the black line using camera-based feedback. That completes our presentation and demonstration. Thank you for listening.